Okay. Well, all of a sudden you went quiet on your own. You're ready. Okay, cool. All right. So a step back, I wanted to go over infrared spectroscopy a little quickly. There are a lot of slides. I'll try to highlight the ones that I really want you to pay attention to and skim over a few other slides. I just want you to be familiar kind of the topic because it comes up quite a bit when we talk about proximate analysis. We do IR analysis sometimes. For online testing, we calibrate using official methods of analysis. So it comes up pretty quite often. So I just want to go over it with you. So you have that kind of the background before continuing with other topics. Okay, so in infrared spectroscopy, there's two zones where we do measurement at. The near infrared, which is close to the red, and its wavelength is between 0.8 to 2.5 micrometers. And then there is the mid-range, which carries less energy, longer wavelength, 2.5 to 15 micrometers. Under infrared spectroscopy, there are different designs of analyses or equipment. One based on dispersive. One is dispersive, that means based on dispersing the light or diffracting the light. So there where we use monochromator, same as with regular UV absorption. One uses mathematical equations, we call them Fourier transform, to convert multiple absorption at multiple wavelengths into a spectra or fingerprint. Reflectance, measuring the light that is reflected or measuring the light that is transmitted. So we're going to talk briefly about different types of infrared spectroscopy. It's used a lot as qualitative, and I'll tell you what incidences, just qualitative, and also used for quantification. So it can be used for both. Okay. So where do we apply IR? I kind of mentioned a little bit about that. So in what instances we use IR spectroscopy? I said it at the beginning. Yes, Katie? Yeah, we can do identification, which I didn't say at the beginning, but that's correct. We can do identification of the presence of different compounds. Quantification, yes. So that's what I mentioned earlier. When we want to measure composition really quickly for quality assessment, for online measurements, we use IR. Very often for dairy, for milk, for cheese, it's quite used for that purpose. For quantification, looking quickly at moisture content, when we produce flour, for example, we need to have certain moisture content. For quality, we quickly, after milling, measure moisture content using IR. During processing of milk into cheese or yogurt, we do look at fat content, protein content. So qualification, identification. There are a bunch, so I'm not going to go through all of them with you guessing. So qualitative detection and quantification. So we can do both. Under qualitative detection, we can do identification, presence or absence. For example, I'm going to give you an example later. Detection of melamine. For example, in baby formulas, IR has been used to identify or detect the presence of. Structure elucidation, we'll talk about later on how we can use certain regions in the IR to elucidate the structure. So looking at certain functional groups that absorb IR radiation at specific wavelength or wave number. so we can identify and break down the structure. We talked about quantification or compositional analysis, considered secondary methods of analysis, because it's based on calibration using primary methods of analysis. Quality assurance, forensic, when you're trying to figure out what's in the product, where the probably certain issue is coming from, so we have to try to identify within IR spectroscopy for detection. Okay, so it's non-invasive. That means you can reuse the sample. Sometimes you just put the sample in sample holder and then take it out. It's not going to be destructive. It's non-destructive, non-invasive method. It's very rapid, quick scan, and you get your results. If it's calibrated, then you have good prediction equations. Minimal sample prep, mostly needs to be homogeneous. If it's a solid sample, it needs to have a certain particle size and consistent so that you have consistent measurement. So it's very suitable for routine analysis. And as I mentioned, I think maybe last time or when, breeders use IR quite a bit because they have a lot of samples from different varieties, hundreds of samples. So they just need to look at how these samples differ in protein content, for example. So they run a lot of samples using IR. Energy efficient, environment friendly, all the good stuff. So same principle. So you have the source of your light, IR radiation, that hits the sample, and then the transmitted light gets to the detector and then converted to a spectrum that we use for identification, or we use the absorption of IR for quantification at a particular wavelength. If we're quantifying, we have to always remember that we need to follow these laws. At a singular wavelength is that quantification is done. However, identification, structure, elucidation can be over a scan of wavelength. So we can get the fingerprint, and no two structures have the same fingerprint in IR. Here's just a throwback in history, trying to remind you that there are 3 levels of energy: the electronic level, the vibrational level, and the rotational level. The IR is equivalent, the IR energy is equivalent to transitions in vibrational states. So we don't see jump from electronic energy levels. We see jumps from different vibrational energy allowable levels. So only compounds that have the exact energy capacity to change vibration level can absorb IR and IR radiation. Again, this is just a reminder that the energy is equal to constant times the frequency. And the energy of the wavelength would be equivalent to the energy absorbed by the molecule, where it goes from ground state to excited state. In IR, oftentimes the x-axis is not wavelength, it's wave number. It's just commonly you have transmittance instead of absorption, and you have a wave number. A lot of time you see that, and the wave number relationship is 1 over the wavelength in centimeters. So the unit is centimeter to the -1. That's how it is, and that's how you would see it. You would see wave number instead of wavelength. So what happens during vibrational energy? So when the molecule absorbs vibrational or IR energy, the molecule vibrates. So basically, I'm not going to go too much into the chemistry of this, but basically you have bending and stretching of the bonds. And with that, electrons are actually moving from one atom to the other. So this is basically how is animated but not much to worry about there other than vibrational energy is basically involved in bending and stretching of the bonds that would make them vibrate in the presence of IR radiation. And just a reminder that a molecule can absorb IR if it vibrates such that its charge distribution changes during vibration. So it's charge distribution between the atoms within a bond. Again, I'm not going to hold you accountable for that. All I want you to remember is that once IR radiation is absorbed, you get vibration of the bonds in the form of stretching or bending. And in a molecule, you have different functional groups, and different functional groups absorb radiation, IR radiation, at different wave numbers or wavelengths. So once you know the wavelength at which each functional group can vibrate, then you can elucidate the structure of a compound. So this is the structure of a methyl aldehyde. So it just each functional group vibrate at different wave number. By knowing the functional group's vibration, you can detect the structure. So that's basically structure elucidation. We use it a lot in proteins as well when we look at secondary structure of the protein and how it's impacted by different processing conditions. So we can look at different bands or different wave numbers and determine how the structure changed due to processing. So these are examples of different groups and what bonds in each group absorb light, and at what wave number this happens. Of course, you don't have to remember all that. It's just showing you that there are different functional groups within different compounds that absorb IR at particular wave numbers or frequency.
And I have a question.
Oh, yeah.
Is this, so this would be the situation from lab when we had isomers, which we would then use. Remember in lab we had.
Oh, we used NMR.
Okay. Okay.
NMR gives us a really good, so this gives you what the functional groups are. NMR gives you where the location is. So this gives you the molecular structure, but molecular formula, but not necessarily how it is located.
Okay.
Where it's located. Yeah.
So it doesn't necessarily tell you about like the primary carbon structure? Or gives you
Yeah, so the
like-
molecular formula is going to give you the molecular formula, but when you draw the structure in space, it can't tell you where the functional group is located. Yeah, good question. We're linking things together. It's very good. IR radiation can be employed for mineral analysis following atomic absorption technique. There? Yes, why would you say false? Minerals are inorganic, that is a correct statement. But in atomic absorption, we are looking at, sorry, I think that's false, but because A is destructive. I'm gonna go with Grace.
There are no bonds.
Yes. Yes, so in atomic absorption, we take the inorganic, you all said correct things. We take the inorganic minerals that are actually in molecules and we get them atomized. We atomize them into gaseous atoms. So atoms in the gaseous state. So there is no molecules, no vibration or anything. They only absorb at electronic level. So they go, only they have electronic energy, they don't have vibration energy. Okay. So mid-IR, the old instruments used to be called dispersive instruments. That means you have a monochromator, the same as what we talked about for UV absorption, diffracts the light or disperse it into different wavelengths, and then you measure absorption at one wavelength. And you can, most of the dispersive are double beam, which you remember with double beam meaning the light is split. We go to the blank cell and to the sample cell at the same time and gets corrected. So you have your radiation source, you don't have to remember any of that. You have the monochromator and you have detectors. Again, don't have to remember that. So, but they're no longer used. Now, the advanced one is Fourier transform. So FTIR, so we hear saying Fourier transform. What is in there? So in FTIR, radiation is not dispersed. So all the radiation gets projected to the sample. And then the compounds within the sample and the functional groups within these compounds absorb the IR radiation. And then the transmitted light reaches the detector. And you use mathematical calculations or Fourier transform calculation to convert the radiation that the detector receives to spectra. So one thing, if you remember this image from when I talked about introduction to spectroscopy, and I told you interference will come back in IR. In IR, the instruments have this interference ability of the light where they project, there are mirrors projected at different angles and different wavelengths can potentially meet in an amplification manner and amplify the signal, or in a cancellation manner that reduces the signal. The reason they do that, sometimes you want to reduce the interference from compounds you don't care for, so you suppress certain wavelengths, and you want to amplify the energy that comes from particular wavelengths that you're interested in for that particular sample. So the way it's constructed is just based on positioning mirrors within the spectrophotometer or the IR to cause amplification or cancellation. Okay, lots of words here. What I want you to know is in transmission, IR spectroscopy is mostly for liquid samples where the light can go through the sample and the transmitted light can reach the detector. But if you have a solid sample, the light is not going to be transmitted through. So we have total reflectance or internal reflectance. The attenuated total reflectance cells. So this is for solids. So basically you have your solid material in a cell and then light is projected on it. It's not going to go through. So what happens, the light is going to go in the sample. Some of the molecules, they are going to absorb light. And the rest of the light is going to be reflected. So the reflected light gives you a fingerprint of the sample based on what the sample absorbed. The internal reflectance, this is a specific cell for liquid samples, and it's kind of the same thing. The light goes through a little bit and compounds absorb, and then the rest of the light gets reflected and goes to the detector using mirrors. Mid-IR can be in conjunction with gas chromatography. So you can have the FTIR as a detector after the chromatography separation, or it can be linked to a microscope as well. So this is commonly used in industry actually for fast. One example, I remember when our industry faculty utilizes this technique to look at crystallization of sugar. And they wanted to look at the crystals and at the same time monitor the IR characteristics of the sugar crystal. So we have a microscope as well as IR. It's very cool, monitoring the formation of crystals in real time. You can use mid-IR for quantification, and this is commonly used in analyzing composition of milk. And here you follow Gauge's law. So you would have to select the atomic, wavelength at which you can measure absorption. So you have to have one wavelength for one particular component. So you have the carbonyl in fat, the amide group in protein, and hydroxyl group in lactose are the functional groups that are being monitored at specific wavelengths for concentration. Of course, we need to calibrate the instrument before we use it. You can use, instead of monochromators, we can use FTIR, but again, we need a kind of a regression equation to select those particular wavelengths to convert absorption into concentration. A lot of math. I'm going to go over this very quickly just to introduce you to Raman spectroscopy, which is a powerful tool in IR. We use it for different applications. Sometimes you have better signal and you can enhance the signal to get better elucidation, structure elucidation. So it's based on scattering of light really. So there is Rayleigh scattering and Raman scattering. So when the light hits the sample, the light can be scattered. So if we're measuring the light scattered by Rayleigh measuring, the one thing you want to remember is that the scattered light has the same energy as the incident beam. So same energy. The other one, Raman scattering, is a little bit different. So the light goes into the sample, and the sample can absorb some of that light and scatter the rest of the light. That scattered light has a significant intensity in Raman, what they call it, and maybe because the person that discovered it is last name. And then you get a very unique spectra for particular structures. So I don't want you to focus too much on this slide, other than knowing the difference between Rayleigh scattering and Raman scattering. Of course, if you want to talk Raman, we need 2-3 lectures to explain Raman spectroscopy. So I'm going to skip this and go to NIR. So in NIR, so again, here the wavelength is shorter. This means carries higher energy than mid-IR. So you can measure composition of solid food, and then the way to do it is diffuse reflectance. That means the light goes in, some compounds absorb the light, and the rest of the light gets reflected and gives you a fingerprint of what gets absorbed. But so there's 2 types of reflectance. There's specular reflectance, and diffuse reflectance. So when the light hits, there's a passive reflectance. You have to hit the sample of the light, and some of the light gets reflected right away. Whereas the other components of the light goes in the sample, diffusing the sample, the compound absorbs a little bit of light, and then they reflect the light after they absorb some of it, and goes to mirrors into the detector based on certain angles. And we don't really care much about geometry, but that's the difference. So absorption bands in NIR mean they're overtones and combination, meaning they're not sharp bands. You don't see sharp peaks. You see like hills. Overtones and combination, they overlap each other sometimes. And the absorption rises from a hydrogen atom attached to a carbon, nitrogen, or oxygen. That's what allows us to determine water, protein, lipids, and carbohydrates. So in water, you have the OH stretch that can be monitored at 2 different wavelengths. The peptides can be monitored also at 2 different ranges. Lipids can be monitored at also 2 different ranges, and carbohydrates as well. But you can see that if you have sample high in water, there is overlap between the water and fat and between water and protein. So we don't see clear differentiation, whereas in wheat and egg white moisture is low, you can see your proteins and fats better than when you have water. So you have a radiation source, don't need to remember. You can also in NIR have a monochromator or interferometer, and mostly we use spectrophotometers and interferometers, and you have a range of detectors which you don't have to remember. Again, measurements is by reflection or transmission. Transmission is mostly for liquid samples, and reflection is for solid samples, but we have to remember that when we're measuring solid samples, they have to have uniform and small particle size. Qualitative or quantitative? Quantitative, don't worry about all of this. It's just telling you you have to do certain regression, multiple regression analysis, which a computer does for you to relate absorption to concentration. This is an example where I mentioned earlier, you have infant formula, you can run melanin alone, and you can determine if you have melanin contamination in infant formula or any other food. NIR can be used for online measurement of constituent during processing. Yes, we talked about that already, but it has to be calibrated so that we can get results very quickly compared to official methods of analysis. Here's just advantages and disadvantages, and I'm going to end here this lecture and move to total carbohydrate. Again, focus on where I spend time, and when I said don't worry about that, means don't worry about it. Okay. All right, so back to proximate analysis and compositional analysis. If you remember with proximate analysis, we said we measure ash, water, fat, and protein. We don't measure carbohydrate because there is not one method that gives me all the carbohydrate, complex carbohydrate that can be present in a sample. So here, the next couple of lectures, I'm going to talk about how you can measure total carbohydrate in a simple matrix, like a juice, for example, that has nothing but sugars in it, and how you can measure carbohydrates, small sugars in a complex sample, starch, and fiber. So we're going to talk about different methods for analysis of carbohydrates. Before we go into that, so the following is our carbohydrate. Yes?
Is that all of them?
Is it all of them? Do you agree with Brittany that it's all of them? Yes? I see a lot of shaking of the head. Is anybody gonna disagree? Yes? Yes. Lignin is not a carbohydrate, it's a dietary fiber, but it's not a carbohydrate because its building units is not a sugar. So its components are not sugar, glucose, or galactose, or fructose, or it is these guys, alcohol. Fumarole, coniferol, phenol, alcohol. These are the building blocks of lignin. It's not digested by our body, by the digestive system, hence, and it's present in plant origin material. Therefore, it is under the dietary fiber component. But not everything in dietary fiber is carbohydrate. So lignin is not carbohydrate. Pectin and cellulose are because they have sugar building blocks. The method used to determine starch gelatinization could be used to determine starch retrogradation. Before we answer this, can somebody define starch gelatinization? You all should know that, and you know it, and you can say it, even if you have exceeded your participation points. Then go for it.
The swelling of starch granules.
What's that?
The swelling of starch granules under added moisture.
Yes, so basically in simple terms, the swelling of the starch granules. So when starch basically is cooked in moist with water, then the granule expands due to absorption of water, and that's when the starch can be hydrolyzed. Okay, raw starch cannot be hydrolyzed. It has to be gelatinized first. Okay, so what is retrograde starch age?
So that's when like your starch starts to cool down and retention bonds slash like process, pushing water out.
Absolutely. Retrogradation is when, after gelatinization, it can happen where your amylose, amylopectin can interact with each other and go from amorphous stage to glassy stage. And then that actually is good for pasta, for example, formation, but it's not really good for bread because that causes staling over time. So can you give an example of, well, no, I'll talk about resistant starch somewhere else, but okay. Can we measure starch gelatinization and starch retrogradation using the same method now that you know the definition? What do you think? Your gut feeling. Why are you scared? It's just yes or no. So Abi, you think no, but it is yes. And I'll tell you later how this is done by magic. You can do both the same method to determine degree of gelatinization and the same method to determine degree of retrogradation. But we'll cover that maybe Friday. I don't think we'll get to that on Wednesday yet. So what's the importance of carbohydrate in food? Why do you care? Why do we care for it? Yeah. It is a source of energy. It's the most important source of energy. Okay, what else? Why do we care in food system?
Like textural slash like mouthfeel.
Functionality, yes, textural. You get starch gelatinization, you form the gel, you get retrogradation, you form that nice pasta. Yeah, functional, test structural, functional. What else, Dora? Flavor? Yes, because if you have reducing carbohydrates, it's going to interact with protein, it's going to give us flavor. And what else when it interacts with protein? What does it give us? By Maillard reaction, what do you get? Brownie. Yes, brownie. Okay, so let's look to see what we have. Main source of energy. Oh, forgot. Source of dietary fiber. Color and aroma. Functional groups enhancing viscosity, stabilizing emulsion by forming a viscous material that can stabilize your oil droplets, gel formation and thickening. Also sugar lowers water activity, so for shelf life, enhancing shelf life. Okay, so the resistant starch. What are the 4 categories of resistance? Quick can. When we say resistant starch, who is the resistant starch? What are they? Did you cover carbohydrate in food chem yet? Yeah, you didn't talk about resistant starch? Valerie? Fiber? Fiber is under dietary fiber. But resistant starch, what are they?
I think it would be 5,
What?
45.
Okay, so the word resistant to what? Maya, resistant to what? To digestion. So which starch will be resistant to digestion? What type of starches won't be digested? Huh?
Insoluble fiber?
Oh, starch is different from
Oh.
fiber. But actually resistant starch can be in the category of fiber, you're correct there. But what makes the starch resistant to digestion?
It depends on type of starch. So it's like the reason I think there's a functional group attached to it makes it so.
You're being just you're overthinking, overview, yes.
The type of bonds, if you can't break down beta bonds, right?
Okay, so we have alpha and beta, and you still can break both based on the enzyme you're using. I'm thinking, is retrograded starch digestible?
No.
Okay, so that's one type. Okay, what else is resistant starch? Yes, thank you. Chemically modified starch. So we have now resistant starch, chemically modified starch. Retrograded, chemically modified. Raw starch. We said the starch that needs to be digested has to be gelatinized. So now we have chemically modified, retrograded, raw starch, and physically entrapped starch that the enzymes cannot reach the granule to hydrolyze. So these are the 4 types of resistant starch. So that brings me to glycemic index. So if you have food that has high degree of resistant starch, they are better for people with diabetes because they're not going to be very well digested. They're not going to release that glucose. It won't increase the glycemic index or the blood sugar. Okay, so we have lots of importance of carbohydrates, and resistant starch can go under dietary fiber category. So why is it important to analyze carbohydrate? Why do we care, Dora? Yes, we need total carbohydrate, which gets by difference. But we need the dietary fiber, so we need an assay. We need total sugar, so we need an assay specific for that. So total carbohydrate, this value is calculated by difference, but we need to determine dietary fiber, we need to determine total sugar. So we have quality control, is always determining changes in quality based on changes in composition. Ingredient authentication, different compound or different, ingredients or different food products have specific concentration of dietary fiber or starch or resistant starch, etc. Composition of information, research. We measure total carbohydrate and small sugars in research. For example, one of my students is trying to induce a covalent linkage between carbohydrate and a protein to enhance functionality of the protein. But we need to remove unreacted carbohydrates. So we need to determine the amount of free carbohydrates. So we really need to run some analysis, determine the amount of total and free carbohydrates. Product development. We are producing a product that is high in fiber, low in resistant starch, or high in amylose, low in amylopectin. So we need to figure out the composition when we are targeting a certain product with certain characteristics. Again, just simple reminder of what the carbohydrates are classified into. We have the monosaccharides, We have disaccharides and oligosaccharides. So di always means 2 units, and anything between di and 10, 2 and 10 is called oligosaccharides. And then polysaccharides, starch, and dietary fiber. Again, dietary fiber includes lignin, which is not a polysaccharide. Just remember that. Okay, so we will be talking about ways to determine mono, di, and oligosaccharides, starch, dietary fiber, and also we will be talking about a general method for total carbohydrate in a simple food matrix. Oftentimes, when we prepare the sample for carbohydrate analysis, obviously it has to be homogeneous, it has to be milled to a uniform and small particle size, and then we dry, and oftentimes we extract the fat. So when I ask you in a quiz or an exam, what are the sample preparation steps you do before any carbohydrate analysis, or starch or dietary fiber or any type of carbohydrate analysis, you would go, okay, I need a homogeneous sample. So homogenize, mill, dry, defat. So remember that. So this is the assay that you will be doing in the lab on a very, very simple matrix product, which is a beverage. So you will be determining total carbohydrate in a 7-Up beverage and also in a beer. Okay, so, but not for drinking. So we're gonna do that using a very common method that is also used for research purposes. So it's good for beverages because there's no other complex carbohydrate other than sugars. So it's good to determine, it can determine total sugars in there. But it's not going to be good for a flour sample where you have fiber and starch and potentially oligosaccharides. So, but it's good for research purposes. Why? Because you often have a purified sample. You have purified, you hydrolyze starch, and then you need to look at the different components, maltodextrin within the starch. So you can use assays such as this. So what is it? Phenol sulfuric acid method. So during this, you use corrosive reagent, which is sulfuric acid. You have your sample, and then you put in the sample concentrated H2SO4. So the concentrated H2SO4 is going to break the bonds, the glycosidic bonds, to give you monosaccharides. So whatever you have in there is going to break your glucosidic bonds, alpha or beta. So it's going to break it into a monosaccharide. And also, what happens when you add the acid, it's an exothermic reaction. It's a concentrated acid. It's going to be very, very hot. So you're going to get a strong acid, you have heat, so your monosaccharides are going to go into ionization reaction and dehydration reaction to give you furans. So your monosaccharide is going to go into become furans compound. So the furan compound is then going to react with the phenol. So you add a phenol, and then your phenol is going to react with the furan to give you a compound in the presence of acid, a compound that can absorb light in a visible range. So you're going to measure the absorption of your sample, but in order to determine concentration, you're going to plot a standard curve. So we usually use glucose to plot our standard curve, but there is a caveat. It's a non-stoichiometric reaction, meaning if you have a fructose versus a glucose, control structure versus right? Control structure, the structure of fructose. 5-ring structure versus 6-ring structure. So that will react differently. It gives you different color, even though at the same concentration, one will be more intense than the other. So if you know that you have fructose and glucose, for example, in your sample, you have to have standards containing fructose and glucose to run your calibration for. That is what it's meant non-stoichiometric, because different monosaccharides might interact differently at the same concentration, gives you different higher or lower absorption. Okay, so this method, like I said, we're going to do in the lab, and it is very easy, but yet you have to be very careful. For example, in the lab, we'll talk about that next week. When you have your test tube, when you dispense the H2SO4, it has to go straight into the sample, not on the sides of the tube, because as soon as the acid hits your sample, the reaction is going to start. So then if one sample goes straight down and another sample you dispensed and it went on the side, you're going to have very, very poor precision. I know, I'm done. I'm going to stop here and we'll continue on Wednesday.